So before I start, I should mention that the real solution to dealing with malicious traffic is to be prepared for malicious traffic. In particular, you should build your links and in your server capacity in a way that allows you to absorb attacks. But in the meantime, because things in the physical world take money and time to change, you need better tools. A little bit about Dyn is we have about 20 data centers in 5 continents. Our main business is DNS services, also email and internet intelligence. And we use Anycast a lot. And some of you may know that we sometimes get some DDoS attacks. So responding to malicious traffic, the old way, or the default way, is first you need to determine which sites are under attack. Then you determine the router names, those sites. Then you SSH into each router. You hopefully type in your ACL in a text editor, and you copy-paste it, and rinse, lather, repeat. You do that hopefully the same way everywhere. You don't make any mistakes, any typos, and you pray. And of course, this is how you feel when you're doing that, because you're under attack, and it's very frustrating. So obviously, you're not as fast as you want to be. You always make typos, always. You forget one router, or you logged into the wrong router, and then you have problems with cleaning up later because you left the ACL in some place, and then you forgot about it. Or if you have automation like we do, your ACL gets rewritten before even the attack is over. So it's just a big mess. Obviously, there are better ways, and we have this tool that I've talked about in other presentations, and it's a continuous integration approach to configuration management, and it works great, except that it's really not built for emergencies. It's more for configurations that are supposed to be permanent. So the approval phase and the testing phase and all that is a bit too much when you're under attack and under a lot of stress. So it's not the best answer. I mean, you could say, actually, you just use templates and generate the configs and push them with Ansible, but still, that's not the fastest way. The way we deal with an attack when we need to filter something somewhere is now through a chatbot. We use Slack, so someone on the NOC channel is aware of what's going on. They know what they need to filter, and they type in some things in this Slack channel. It's a lot shorter and more concise than what you would have to do at the CLI, and you only do it once. And while you're doing it, everyone is watching what you're doing, because you're doing it on the Slack channel. And so you type that, commit, and sit back and relax, and you watch your counter graphs to see how much you are filtering. And that happens very, very fast. Even the sloth from Zootopia would do it fast enough. So what is Flowspec? Because that's where I'm going. Flowspec is a standard. It's been around, I think, from 2009. There's an RFC that you should read about it. It allows you to specify not routes, but filter specifications, or ACLs, basically. And based on those ACLs, you can you have the option to do several operations on those packets that match the ACL. You can discard them, you can apply a rate limit, you can redirect the packets to a different routing instance, etc. It's very cool. So we thought, okay, let's build something with Flowspec that we can use quickly. And so we've used ExaBGP. Everybody probably knows what that is. It's a BGP tool that is open source. It's great. We use it for other things, and we thought, well, let's just put an API in front of it, make sure that the API allows us to specify these filtering rules and put some persistence, some storage, so we can save them, and then we have that exabgp instance talk to every edge router in our network, and then that opens up a lot of possibilities. So with an API, as you know, you can do many things. You can talk to it directly from a command line, or you can tie it to a chatbot, or you can build a web page that talks to the API. If you're brave enough, you can even tie it to your NetFlow collection, and if you are very sure about what patterns you are encountering that make sense and you want to block, then you can set some triggers that talk to that API and actually block things for you. So in our case, we built it. We put the API server in one of our core sites. We just configured a peering with that API server from every edge router. And you can actually also do redundancy very easily by just placing the same thing in a different core site or this different part of your network, and use Redis replication to exchange the data, and just peer with the other one at the same time from every router, and it would look something like that, right? Very simple. So going into detail, if you haven't seen exabgp configuration, this is probably very intuitive. Doesn't need a lot of explanation. You define a template that you can reuse more easily, and in the template you put all the common parameters that you're going to reuse in your neighbor definitions, and then of course you're going to define all your neighbors and inherit from that template. And here's the fun part about exabgp. So you can define a process, you give that process a name that makes sense to you, and that process runs a piece of code. In this case, it's a Python piece of code. And you define the encoder as JSON, which means that you're going to be exchanging JSON. What that does is the exabgp daemon will run this application, and it will be mostly receiving the standard output from that application and taking it in and passing that data to the BGP engine. From the other side, and I'm just giving Juno's example, but it could as well be another vendor. Very similar, just a BGP peering. It's an external peering, in this case, local address, PRAS, neighbor. And notice that this is a multi-hop session. The reason for that is our network is a bunch of islands. We don't run iBGP in between our edge sites and our core sites or anywhere, actually. So the easiest way to implement this was to just put the API thing in one place and make it just peer doing multi-hop, eBGP peering. The part at the bottom that says no validate, if you've read the RFC, it'll make sense. But if you haven't, very quickly, there are some mechanisms defined in the standard that try to protect the receiver of the Flowspec in a way that doesn't compromise someone else's routes or someone else's traffic. And for example, if you're a service provider, you would probably want to only accept Flowspec definition that matches a route that same peer is sending you. In our case, that doesn't apply, so we use the no validate option. But you do have the option to specify a policy, so you can do anything with that. Some options, for example, you can limit the amount of Flowspec entries that you accept, or you can limit the prefix length that you are able to accept, or that you want to accept. And the application itself is simple. It's a little bit of Python using the Flask framework. It's a web framework you can use for APIs or for anything really. The persistence layer, we chose Redis because it's simple, it's fast, it's well known, and it allows for replication. And then there's a simple reverse proxy, so we can do SSL certificates and authentication. Now, going more in depth into how the REST API works, there are these resources. So as you know, a REST API, probably everybody should know what it is by now, but in case you don't, a REST API is based on resources, and in those resources, you can execute operations, and those are usually post, delete, or put. So you can create new resources, delete resources, or modify resources. The resources that we created were three, very simple. Flows, which are the specifications for those ACLs, and they actually can represent more than one flow spec. You'll see how. Then there's sites, because we didn't want to have to type all the neighbors in our commands. We created this mapping between sites and routers, so it's easier to just say, apply this to NYC instead of saying, you know, router 1, blah, 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 blah. And then there's the refresh resource, which has to do with the fact that if the XWGP daemon goes down, or if one of the routers reboots, that session is reestablished, and maybe if your, what's it called? The, let me go back. Did I miss that? The timer, what's it called? The graceful restart, saying my memory. If graceful restart has expired, then you need a way to refresh that route, that flow spec definition. And that allows you to send it to all the routers affected by that rule. The flow resource is a n-tuple thing with all the possible parameters for matching the packets. We did not include all the possibilities. There are more, like packet length and ICMP code and a bunch of little details that we thought, well, we'll start simple and then add on. So these are the parameters in the flow resource. It has a name. We usually name it after the incident that's going on. The neighbors can be sites or routers. The operation is you're either announcing or withdrawing. You have source IPs and or destination IPs, protocol, source and destination port expressions, and those are based on the RFC syntax. And optionally, a rate. So by default, we discard packets, but if we pass the rate option, then the packets are rate limited. This is an example using curl. So speaking directly to the API from a command line. The header says content type is JSON. The operation is post, so we're creating a new resource, a new flow resource. We name it example flow. It has a list of neighbors, site 1, protocols, TCP, 2 source IPs, and 1 destination IP. And then the ports are port 80 and port 443, and a rate. Once the flow is created, you can query the API and see that everything you passed it is there. And you can see it in nice JSON output. And this is what XWGP receives. So once the flow spec, the flow resource is stored in Redis, then it is converted to this JSON format that XWGP understands. And you'll notice here that it creates 2 flow spec definitions, 1 per source, because the standard says that you can only have 1 source and 1 destination. So the code is smart enough to separate it into 2, and that is passed on to XWGP. Notice that here we are telling ExaBGP which neighbors are supposed to receive the announcement. So in some cases, you don't want to send the, because we specified the site previously, that means that we don't want that rule to go everywhere. We want it to go to a specific router. So in this case, the routers are these two. And that is a great feature in ExaBGP. And then in Junos, you can actually see when that Flowspec is received, you can see that the filter is created. And like any other filter, you can look at counters, packets and bytes that are discarded or that match the rule. So far so good. We have the API, it's working. Now, how do we use it? I noticed this trend that operators really like chatbots because it has many advantages. And so in this case, the chatbot is our interface between the people that are on the Slack channel and the API. It's more human-oriented. It adds some help output. So if you forget the syntax, and of course you forget the syntax every time you need the help. So you say, remind me please how I specify a flow. It has a dry run feature, which is cool. You can see what you're doing, get some validation before you actually commit. Everyone in the team can see what is happening. I think that's the main benefit. Before chat ops, we were used to typing things on the command line and then posting it on the chat so everybody knew what we were doing, but that's 2 steps. This is 1. And the cool thing is with the same chatbot, you can talk to different APIs that do different things, and in fact, that's what we do. And when we asked the people who are at the forefront of dealing with these issues, they were quite happy. So the response was good. The experience was between February and July, we used it about 150 times, and this is an informal count based on a search, which means that we were, using it quite a bit. No more CLI typos. The reaction time is reduced significantly. I'm talking about going from 15 minutes to under a minute in reaction time. And because we name those flow records after the incident, which is tracked in a different application, then when that incident is closed, you can actually delete the record from your API. I did an informal poll on the chat. How much faster do you think that you can deploy packet filtering now compared to before? And everybody agreed that it was a lot faster, which is good. We had some challenges. ExaBGP is great and is very featureful, but as someone who maintains open source, I know it's hard to maintain documentation. So sometimes it was a little hard to figure out how things were supposed to work. But we figured it out. At the time, the multiple neighbor functionality wasn't there, so we had to do a lot of reading code, and we noticed that it was actually implemented in the master branch. So there was code and it worked, so we were able to use it. I think by now the latest release includes that feature, so that's great. One thing that we haven't tackled is the IPv6, and that's unfortunate, but it requires Junos newer than or more recent than 16.1, and that's not always possible, so it's something that we will definitely tackle when we can. Before taking questions, I wanted to mention and thank Jeremy Dobbins-Balklad, who helped me a great deal with the API implementation, and Johnny Graves, who basically took the task of developing a chatbot, and so both of them did a great job. And we have quite a bit of time for questions. Maybe some closing remarks before I forget. This isn't rocket science. I'm sure some other people have done this internally. But I really wanted to show how it's possible. It's not hard, and I gave you all the hints. All the hardest parts, which were, okay, let's figure out the syntax that we need to pass on to XMPGP. I figured it out for you, so you're welcome. Hopefully, this will help others implement something like it and benefit from it. Michael.
Michael Sinatra, ESNet. Very interesting what you're doing. Sorry for my froggy throat. What kinds of security implications are there in this setup? I'm thinking in terms of like, how do your operators authenticate to Slack to make sure that it's actually the person who's authorized to be doing this?
Yeah, great question.
Are you doing two-factor on Slack or anything like that?
Yes, right, great question. So we run Slack internally, first of all. So it's not going out on the internet, and we do use 2FA, and the chatbot also checks that only people from the NOC are able to use it.
That actually answered my next question, which is what do you do if somebody's DOSing Slack? But
yeah, I actually don't even have access to the bot. Of course, I have access to the real server, so I can circumvent that. But it's pretty tight. Yes.
So Aaron Finney with OpenX. Question is, what are you using for your DDoS detection right now? What tools? And do you have any plans to integrate those into this for orchestration?
We use a lot of tools, but we use a lot of NetFlow. So we have a lot of nice dashboards and searches. We use Elasticsearch to store our flow data, and we've created triggers that very quickly tell us that a particular IP is sending too many packets, or a particular IP of ours is receiving too many packets, and so we detect attacks pretty quickly. We have not tied that to a direct action because I think we're not there yet, but also because our NOC is, they're very quick in deciding and running tools, so it hasn't been a big priority, but it could be done.
Do you currently have 24-hour NOC coverage?
Yes.
Who's watching this?
Yep.
And then what's your average time from the start of an event until you actually detect it and make an action on it?
It's much better now, I can tell you, than I don't know, years ago. I don't have the data. I mean, I would have to ask people from the NOC, but I do know that it's way faster because we're better at using tools and developing tools now.
Fair enough. Thanks a lot.
Thank you. All right. Thanks so much.